Om Shri Gurubhyo Namaha Hari Om. Om Sahana Vavatu Sahano Bhunattu Sahaviryam Karavavahai Tejasvinavadhitamastu ma vidyushavahai. Om Shanti Shanti Shanti. Om Asato ma Satgamaya Tamaso ma Jyotirgamaya Mrityo ma Amritam Gamaya. Om Shanti Shanti Shanti. Om Sarvesham Swastirbhavatu Sarvesham Shantirbhavatu Sarvesham Purnam Bhavatu Sarvesham Mangalam Bhavatu. Om Shanti Shanti Shanti. Om Lokaha Samastaha Sukhino Bhavantu Lokaha Samastaha Sukhino Bhavantu Lokaha Samastaha Sukhino Bhavantu. Om Shanti Shanti Shanti. Om Purnamada Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya Purnameva Vasishyate. Om Shanti Shanti Shanti. Om Shri Gurubhyo Namaha Hari Om.
Okay, good morning, everybody. Except for one person, I was able to talk to everyone, the Viva. So there are a few things that I found out, as I suspected. There is some cross correlation between the work of the people, and I really appreciate some of them admitting so that they refer to or whatever. So I like to discourage, but given the opportunity, one wants to go advance. So you will be tempted. It's very difficult under the circumstances to avoid the temptation. But I encouraged you to do it independently as much as you can. But I can see that a number of you are deficient in fundamental understanding. So I'm going to go through the two problems that I asked this morning. One was the variation. The reason I got the same problem I asked, the two problems were asked in two consecutive quizzes. Similar problem. Like one was the film curing a film on a substrate. The other one was the defroster on an automobile. Both of them are similar. You can use electrical circuitry to really solve the problem, but it's a little tricky. But I just had made a small variation, and I could clearly see those who submitted very quickly, they could not do this. They could not even proceed an inch. So you can clearly tell there is some issues with I don't know. I'm still thinking about it. What I'm thinking about is I will still continue to give these problems. Maybe multiple choice and submit your procedure. And time will be a lot shorter, so you will not have any chance to really check on somebody else. And another funny thing is, one shared the knowledge with another one, and they both had made the same mistake. And that happens often if you copy from somebody. And the one who let the other guy copy did not admit to it, but the other guy who copied admit to it. admitted to it. Interesting. So this is how forensic evidences are collected. But I'm not going to be angry with you guys because I think there was an opportunity, so you took the opportunity. But I just resisting that is going to be a tough thing to do. But I don't even know how. Maybe we can make a 7 team out of the 14 people, and you do the problem as a team, and maybe as a competition, whoever comes the first 4 or first 3 gets a prize or something like that. So then you will not let the other guy copy it. I don't know. I think the most important thing is when you come out of this class, you should know some fundamentals of heat transfer. That's my hope. It doesn't matter whether you knew it brilliantly or you did very well. I may get some laurels, but I'm not looking for that. I'm looking, have I given you enough information that you can use it later on in your life? And have I given enough exposure to some theoretical and practical knowledge that you can use it later on? That's all my hope. So any suggestion that you have how to improve this are welcome. I did have some network issues. Now I see some bad network right now. Do you hear me now? Well, I don't know how many people are there in the audience.
Yes, sir.
So, okay. All right. So, so you don't have, Murali Krishna doesn't have any issue with the networking? No issues.
No, sir, no issues.
All right. Okay. So I asked 2 problems. Most of the guys, I don't know, I could ask, I think the fin problem, I will go through that again, once again, what mistake people are doing. Okay. One problem, I got a variation of what happened there? Oh, sorry. I have not even connected this. That's what happens. Okay. All right. Sorry. Okay. So I asked, can you please mute your audio?
Sorry, sir.
Okay. So this is the film. All right. So the junction temperature has to be some sort of a TC for this to cure. So this is a substrate. And the film length is, this is TC here. The film length is LF and the conductivity of the film is KF. It's very easy. This is H and the temperature is T infinity. There's some air going through. So it's cooling off. So the earlier problem was I heated the substrate with a Q and I keep the outside temperature of the substrate TS, and I don't know the film temperature on the top. I don't know that. But this is the junction temperature of TC. So this problem is very easy to do in an electrical circuit. So let's just do that. So basically, this heat is escaping through this, the conducting through this, and then convecting. So there are 2 elements are involved. So let's just do 1. So here this was T infinity. And it's 1 over HA. See, A is going to be 1 area per unit area. So I'm going to assume unit area to be 1. So H is this, and there's this. If I heat this one directly, there's another resistance involved from the conductivity of this. So it's basically LF over K. Okay, so and this is where I heat. My Q is coming. All right, here I go outside, I escape. So this is the TS temperature, and this is TC. And this will be L substrate divided by Ks. So I can easily solve this problem, get it. However, so this is only when this substrate is transparent. suppose I can only, is it not a it's an opaque material. So I'm heating it here. TC is there, but I'm not heating here. So this is TF. I don't know the TF. I don't know TF. Okay. So there is a Q. So this is a Q coming in. The Q1 escaping to the air and Q2 escaping to the outside. I don't know TF. So how will I solve? That's the difference between this problem and this problem. The only thing is, I know Q2 is going here as well as Q2 is going here. So this is TC. This is not changed. Okay, so I can get Q2 from knowing TC. What is the Q2? Q2 is, what is that? TC minus TS divided by LSKS, which is same as this. So Q2 also is same as TF minus TC divided by LF over KF. Okay, since I know Q2, everything is known. The junction temperature is known. Outside the substrate temperature is known, and everything is known. So Q2 is known. So Q2 is known here, and I know TC and I know all these quantities. So TF can be obtained. So TF H multiplied by TF minus T infinity is going to be Q1. So Q1 plus Q2 is Q. So just small variation becomes a little complicated because you don't know this. See, advantages of doing this electrical resistance is many times you don't have to know this. The middle temperature, you can get the total resistance, but unfortunately, I don't know this, so I cannot do that problem. So you got to do it in a separate way. So many people couldn't get this one at all. So anyway, I'm just explaining. Are there any questions on this? So there is just a small variation, make some difference here. You got to use the fundamental principles to solve it. But electrical circuit does help you. It tells you exactly how the Q2 is going. Q2 is going. There's no heat here, so Q2 is going here. Okay, understood this problem? Any questions?
Yes.
Any question? Anybody? Anybody? Please feel free for any questions if you didn't understand any concept here. Okay. All right. Now, other question is that I was asking about a hollow sphere. I asked two different problems. So inside radius is Ri and outside radius is R0. And Ti, so T0 and Ti here. So first problem was, what is the temperature distribution in this space? So if I do the temperature distribution question is asked, immediately I know the conductivity in steady state is del square T is 0. So in spherical coordinate system, the del square is 1 over R square, T over dr, R square, T over dr. That's the operator. All right. So I need to solve this is equal to T0. So then what happens? R square dt dr is a constant. Okay, then you can take differentiated both sides, go to 0. So dt dr C over R square. Integrating again, T of R is minus C over R plus D, some other constant. So knowing the TID and OD, I can calculate C and D. But that doesn't, if I ask you, okay, so this is to solve the temperature distribution. However, suppose I want you to know what is the thermal resistance of the hollow sphere. How will I do that? Now, it's advantageous if I give a thermal resistance, either it could be a sphere or it could be a hollow cylinder, it doesn't matter. It's advantageous. Let's say I have a hollow sphere and I have a hole here. So I take, this is Ri, the radius, and I take an arbitrary radius R and I formulate the heat. So remember, in a steady state heat transfer, the integrated heat that's escaping this whole sphere at any radius are the same. That's key. That is the important thing. So minus K, look at the Newton's law. Minus K, area 4 pi r squared dt dr is Q. Remember, when I talk thermal resistance, I need Q divided by, or T delta T divided by Q, whichever way. So to get the resistance. So, okay, so let's do the dt is equal to, Q is a constant. The heat at any radius is going to integrated heat is a constant. That doesn't change at that particular radius. So this is dt is dr Q dr divided by minus 4 pi k r square. Okay, I follow. So I integrate from inside to a particular radius. So it's t inside radius to t is equal to q is minus 4 pi k. dr over r square is minus 1 over r. And I vary the between ri to r naught. Okay, so becomes q over 4 pi. This becomes plus 1 over r minus 1 over ri. Okay. So t is higher inside. Yeah. So here the t was lower. So this becomes negative. So that is the reason it becomes okay. So delta t, positive delta t, becomes q over 4 pi k 1 over ri. Let's just go to all the way to the outside. Okay, 1 over r naught. So delta t is, so what is my thermal resistance? T I minus T naught divided by 1 over 4 pi k 1 over ri minus 1 over r naught. So that's a thermal resistance. I'm sorry, thermal resistance is this. This is the Q. Okay. Yeah, that's right. So I'm just dividing everything by 100. So this is the thermal resistance. Okay, so whenever thermal resistance is asked, it's advantageous to use this equation because it gives you directly T and Q. That's the reason. Okay, how will I do that for a cylinder? Okay, let's just let's do that also. Okay, let's just, okay, so I have a cylinder. If it is a full cylinder, what happens to the temperature distribution? Anybody knows? What is the distribution of a full cylinder in the along the radius? Anybody? It has to be constant because the logarithmic thing goes infinity here. So that constant is, so it has to be in a sphere as well as in a cylinder. If it is not hollow, it has to be constant. It has to be uniform temperature, the whole thing. So let's assume this is a length L. Remember, I'm trying to get the this thermal resistance on a cylinder. Okay, so same way, I'm going to assume a particular radius R. So, okay. So what is the minus K? 2 pi R L, that's the surface resistance, multiplied by dt over dr is my Q. Okay, all right, so that's Q is a constant. So what happened? dt is Q divided by 2 pi K, 2 pi K L dr over R. So I integrate from some known temperature I to temperature T. So this is Ri to R. So Q 2 pi KL log R over Ri. Remember, Ri is small, so this becomes big. So this is that's correct. Okay. So, and here T minus Ti, so R naught is higher. So let's assume R naught. So this is R naught is, let's see, this is not correct. Okay, that's fine. So this is T minus Ti is delta T. So the thermal resistance is log R over, or whatever, R naught over Ri divided by 2 pi K. So because you need delta T divided by the resistance. So different, this is like 1 over 2 pi KL, 1 over divided by 1 by 2 pi KL. So this is divided by resistance. So this is the resistance. And the log R naught or R naught comes in. So that is how we got the thermal resistance of a cylinder is, in a steady state problem. They're all steady state problem. Let's say if I have this situation here, so I have a slab here of thickness L, conductivity K, the slab, and there's a fluid going here. So T infinity, and there's a heat transfer. So it's something like this, and then there is a heat transfer here on this slab, and then again another heat transfer. So this, let's say, is 1 and 2, and this is T infinity 1 and T infinity 2. This is K. So how will I write the circuit here? How will I write the circuit? Between, I want to know the Q to T alpha 1 minus T, I'm sorry, infinity 2 divided by the resistance per unit area. So how will I do that? So it's nothing but 1 over H1 plus L over Ks plus 1 over H2 per unit area, of course. That's it. So it's very simply done. I don't have to know the temperature here or here. You can find out the temperature once I know what Q is going. So the same heat is going through here, here, everything. So I will, if I ask you what's the temperature at the entrance and the exit of the block, I should be able to tell. But this is how you write it. You write the total resistance. This is how the same problem that previously I gave you. Same heat is not going through. In other words, in your film problem, the heat is escaping from here. So this is the same heat is going. If I heat it here, there's one heat is going this way, other heat is going this way. They're not the same. Here on this particular problem, the same heat is going through, transmitting into the solid, and then going to the fluid again here. Okay, same heat. And that is the reason you're able to sum the resistance. They are in series, you're able to sum the resistance. Understand? Any questions on this? So you should be able to do some of this fundamental problem. And I tell you, unless you do problem from the book or wherever the source is, one gentleman was telling me about, he referred to some YouTube to do some problem. It's good resource. I don't have any discouragement at all, but it'll be a time consuming, obviously, unless you know exactly where to go. Okay. All right. Now, I just want to renew our convection. So if there anything in conduction that you need to resolve, you can, from a group of you, can formulate some questions, come and email me or text me through a chat in Teams, and then I can look it up and then come back and discuss, So that way there is a two-way communication. It's not only one way. So if you find some area that you would like to explore a little bit more, please feel free to consult among yourselves and come back. And about the forming of the teams, you want me to form a 7-team member or 3 team per that doesn't come out with the 14 people, whereas 2 people per team, 7 teams seems to more workable. And I hope both will share responsibilities to do problem, to do project and stuff like that. So consult among yourself, poll, whatever you want to do, democratically find out what is the major opinion. So let me know. Okay, so I'm not going to decide for you guys. You decide for yourself. So, all right, we'll maybe talk next week that what did you decide. So in the meantime, if there's any topic that you would like to explore a little bit more, please feel free. By the time, hopefully by next week, I'll have one more quiz. So I want to conduct maybe every other week, maybe, but we'll see. I have to think about what, because of your performance and stuff like that, I need to insist on some fundamentals much more. So I need to go back from the beginning and then ask much more fundamental questions. So keep on refreshing it, do problems, If you're spending 2 hours a day, I would say one hour to review and another hour to do problem. So you make mistakes, so what? So that don't worry about that. So, okay. Now, where we are here in convection, forced convection basically. So what are we trying to do? So what is objective in forced convection? Anybody? What is for a heat transfer expert? What is his objective? He wants to find out HTC, isn't it? That is his whole objective. How do I, knowing the fluid mechanics, the fluid behavior, how will I find out the heat transfer coefficient? Now, heat transfer coefficient, again, you need to define, it's an interface between a solid, it's warm or cold, it doesn't matter. So how is that heat transfer is occurring at this boundary between the fluid and the solid? That's where the heat transfer coefficient definition comes in. So the first step is we need to solve procedure. The fundamental equation of fluid mechanics and do appropriate approximations. Appropriate approximations. What are the approximations that I'm making here? One, steady state. Two, what's it two? Two-dimensional. Three, laminar. It's not turbulent at all. Four, fully developed. So fully developed means the entrance effects are all disappeared. There's not going to be any changes to the velocity, mean velocity at all. It's going to be stable. So that's what this means. Okay, these are all the approximations. So what are the equations that we saw yesterday? What's first one is the continuity. Is du, my vector, velocity vector is u and v. W is 0 because two-dimensional. So u, if I put an arrow on top, means this is a vector. So du dx, dv dy is 0. That's a continuity equation. Okay, how about the momentum equation? Okay, so I'm going to write momentum in general and then approximate it. So because it's a steady state, the only thing we got is u dot del u is minus 1 over rho del p nu del square u. Okay, so and that's only one because v is 0 identically, the approximation, and then d over dy I'm going to assume to be d over much more than dx because the boundary layer is where a lot of action. So I need to find more. So d over dy is much sharper than d over dx. So that's the approximation I make. So what do I get for the momentum equation? Is u du dx well, it's not, v is not 0. For a pipe flow, it's 0. So v is not 0. Pipe flow is 0, but v is not 0. V doesn't change in x direction, that's all. So v du dy is minus 1 over rho ep dx plus mu del square u over dy square. So x square is eliminated here because this is because of this. So this is my momentum equation. And how about energy equation? It's the same as the heat transfer, except your time derivative is the total time derivative. So what happened? You get u dt dx plus v dt dy is alpha d square t over dy square. Again, I'm eliminating that d square t over dy square here. So this is my energy equation. So this is the momentum equation, the energy equation. Everybody followed that, and this is the continuity. Any question on that? Okay. All right. If that is the case, let's just go back and look at where we are in the presentation. Okay, the first problem. Okay, so what I did, this is where we stopped yesterday. Okay, so I'm going to explain it here. Okay. All right, so what I did here, I did a very simple non-dimensionalization of what happened there. Huh. Funny. I tell you, I don't understand sometimes Mac myself. Okay, all right. What am I doing here? I'm just dividing, non-dimensionalizing all parameters. The distance parameter is non-dimensionalized by dividing by the length of a plate, some characteristics dimensions. I'm doing everything same for velocity, pressure, everything. I'm performing a non-dimensionalization. If I do that and apply the three equations, I find all the quantities are non-dimensional except there are parameters appearing on the right hand side. And the momentum equation, it becomes 1 over the Reynolds number based on the length of the plate. And the energy equation not only is dependent upon the Reynolds number based on the length and also the Prandtl number. Prandtl number is the ratio of the kinematic viscosity, which is the diffusion of velocity, and divided by the thermal diffusivity, which is a diffusion related to the diffusion of thermal energy. That's all. So, okay. So what happens? Quickly, I can tell my solution. So based on this, let's look at this. So U is a function of, here I find V, I can bring it to the right hand side, will be a function of U, X, and Y, isn't it? I mean, it's very simple to do because I know everything is non-dimensional, no other terms are involved, only V, U, and X, some function, some arbitrary function of, so V can be determined from here, okay, from this equation. Has to be some arbitrary function of U, X, and Y. Those are only parameters I see. And how about looking at the second equation? Okay, so second equation, I need to know the u prime. So v prime, I know that is x y and then u prime. So I'm just going to so this is going to be a function of x and y, of course, non-dimensional, plus there's a Reynolds number coming in, so that's a function of Reynolds number, plus the temperature, the pressure gradient. Pressure gradient is important. So I equated the u to be from this equation because v is known from here. I substitute v here. So what is u will be at some arbitrary function of x, y, r. That's all. I don't know what the functional relationship is, but I can tell from the behavior of the equation, it has to be some arbitrary function. And similarly, why did I do this? So I stopped this. I did not proceed further. Okay. Okay. Now we know that u and v are given here. Okay. How about the stress friction coefficient? You know, friction coefficient is going to be mu du dy. Okay, on a plate. So I convert that again non-dimensionally. Mu u naught, u over u naught, I multiply over L y over L multiplied by L. So that's how I get this. So du over dy is non-dimensional, that y is equal to 0. That is where my stress is. So what happens? I can define this as a non-dimensional, let's see. So it's basically a function of what happened here. What is this? This is nothing but if I multiply this, this is a stress. So if I multiply by this L square, then I know I can convert this Reynolds number, but that's okay. A coefficient of either the drag or the friction, whatever, this is a coefficient, is given by definition is the stress, shear stress divided by the static head. This is this rho u square over 2. This is the dynamic, dynamic pressure head. Rho u square over 2. That's a definition. So again, I apply the non-dimensional parameters here. I find this to be equal to, see, tau as you know that it's, okay, so let's do that. Let's do that. Because if I quickly do that, you guys won't follow it at all. Okay. Okay. Okay, so my tau, the shear stress is given by some mu ul over L du over, these are all non-dimensional, okay? This is not, they are not they. This is not non-dimensional. So this is dimensional also. But the coefficient of friction or drag or whatever based on the x distance is given by the shear stress divided by rho u square over 2. So that, let me put that one, just mu u infinity over L du dy y is equal to 0. They're all non-dimensional, okay? I just put it. So divided by rho u square over 2. So u square and u just cancelled. Okay, mu over rho is nu. So 2 du over dy, non-dimensional, at y is equal to 0, divided by, this is nu, mu over rho is nu, q log L. So this is a non-dimensional number. What is that? 1 over Reynolds number. Some 2 over Reynolds number based on length L multiplied by du over dy. Again, non-dimensional. So what is that supposed to mean? I find in a general case, okay, since u is going to be a function of, so I'm going to have dCfx, 2 over Reynolds number L. And we know earlier, if you look at the earlier page, du over dy. So we knew what is du over dy. So let's look at the earlier page. So u is a function of xy Reynolds number dp dx. Let's assume that there is no pressure gradient for the time being to make the problem a little bit easier. If that is the case, I find the coefficient of friction to be some arbitrary function of x prime, because remember, I put y star is 0, so y has disappeared from the problem. Okay, so it'll be a purely function of x prime, x and an REL. So simple dimension analysis has given me that coefficient of friction has to be inverse of the Reynolds number, and some factor is a function of Reynolds number. So see what happens here. If I want to conduct a test for this friction, okay, I want to get this plot. So I know for various x prime or whatever at some location, if I know the Reynolds number for the test, I can find out exactly where the CF is going to be. Okay, where as a function of Reynolds number, how does it vary? So I know that the performance of this function f and so on. So the dimension analysis, even though it looks rather simple, it has a lot of importance, giving you some interpretation of the real behavior of a phenomenon. Okay, so let's go. Having seen that the stress is related to the Reynolds number, I'm going to do a problem. Okay, just to illustrate that relationship. Okay, here the flow is going to be over a curved surface. Okay, it's still, let's assume laminar. The local shear stress is given by the relation. So shear stress is given by this, some 0.3. This is basically some sort of a if I take 1 over Reynolds number square root, that's what almost becomes like this, because you can bring this inside here and so on. So some sort of function of this. Let's go here so that we get ready to explain that. Okay, so you know CFX based on X is the shear stress at the wall based on the X divided by half rho U squared. Okay, so he has already given the shear stress to be 0.3 multiplied by 2, so it'll be 0.6 rho U over X to the power of 0.5 U infinity to the power of 1.5 divided by rho U squared. So this should be U infinity. Yeah. Rho mu, I'm sorry. So not velocity divided by X. Okay. So I can manipulate all that. It's not difficult. I manipulate all this U infinity 1.5, everything like that. So I get 0.6 multiplied by mu over rho U infinity X. So this looks like 1 over Reynolds number, isn't it? Based on X distance. So this is 0.6, 1 over square root of Reynolds number based on X. Okay, so that's really, so since it's also based on, so the average, whenever you get based on X, the average you say you integrate over the length divided by the length. So it cancels out. So you integrate that with respect to X. If I perform that, I find the average friction coefficient on the plate, given that behavior for the shear stresses, some constant 1.2 divided by the square root of. So the average frictions, typically you will find this to be to some sort of a constant. This is 1.2 in this case, square root of. This is a Reynolds number based on the length L. So what's the Reynolds number based on L? Is U infinity L over mu. Mu is a kinematic viscosity. Okay. Any questions on that? So this is just an illustration. So given the shear stress, maybe they measured it somehow. How will I get an average shear stress, and how this related to the Reynolds number, square root Reynolds number, whatever, 1 over square root. So very high Reynolds number, you find the drag is much less. That's what it tells you. So, okay. Any questions on that? Okay. Okay. Let's go one more step, just so that to illustrate the power of the. I started the momentum equation, did not do very much to the energy equation. If I perform the energy equation, so what do I do? So basically, my heat transfer coefficient, so let's just, let me just do this one here. So I'm going to do the similar one on the Nusselt's number also. So let's just do it. So heat transfer coefficient. So what is the, suppose I have a plate and I have a temperature. This is the temperature of the T infinity, and it's a hot. So this is a TS. So what's the heat transfer to from here to here is minus K dt s over dx dy. This is y, and y is equal to 0. Okay, so that t over ty. I'm sorry. Okay, so what I'm going to do here, I'm going to non-dimensionalize everything. So if I non-dimensionalize, this is the fluid, by the way. So it's kf over the length of the plate. So I non-dimensionalize y prime, y as y prime. And then I need to non-dimensionalize the temperature also. I'm going to divide that by T infinity over Ts divided by Ts minus T infinity. And then dt over dy. All right, I'm not sure why there is a, oh, I see. I need to divide and subtract. Okay, that's fine. So basically what happened here, it becomes, because this is negative, T infinity is lower than Ts, this is negative, so it becomes plus. So I get, I'm defining Kc as Kf over L dt dy. I don't want to scale it. In other words, this is the heat transfer. This is nothing but H multiplied by the delta T. That's the reason this came. So the Ts minus T, this is T infinity here. So the H is defined as the Q divided by Ts minus T infinity. That's what it is. So that's the reason that that thing came, and this becomes 1 because I non-dimensionalize the temperature and then I put the definition for Hc. So that is the reason 1 was minus, and then so this becomes minus. So I this gets cancelled. It will be 1 with a minus, so this becomes plus. So my definition of heat transfer coefficient is dt over. So if I want to put this is dt dy. So what is Hc is Kf over L dt dy. All are non-dimensional, okay? So what is Hc? L over K. This is the definition of Nusselt's number, which relates to the heat transfer coefficient, the conductivity of the fluid, and the characteristic dimension L. That's what that is. So Nusselt's number is dt over dy. So from looking at this, I can tell that Nusselt's number is going to be a function related to, obviously, y prime is gone. So x star and some sort of a Reynolds number, because remember, it is dependent upon the velocity. So Reynolds number and the Prandtl number. The energy equation has got Reynolds number and the Prandtl number. So the Nusselt's number will be some function of the relationship of the distance x, which is non-dimensional, the Reynolds number based on the length L, and then the Prandtl number. So if I take average over x, okay, x is disappearing. So if I take the average heat transfer coefficient based on the length L, then Hc over Kf is the definition. It will be purely a function of Reynolds number and Prandtl number. And this particular experimental curve illustrates that. Okay, so look at this here. So this is for Nusselt's number. I'm going to divide that by PR to the power of 0.3, so to normalize it. It's going to be a function of PR to the power of 0.3 from experiments. So let's say I want, this is a very low Reynolds number regime, 3 to 100, that's all. So I find all the data that people have done over various fluids in cross flow over pipes, wires, and circular cylinders. If you look at that as a function of Reynolds number is based on the diameter rho u over. So this is basically Reynolds number directly based on the diameter for the various geometry. And if I plot the Nusselt's number divided by PrO3, I find it to be almost like a constant, maybe 1, and Reynolds number to the power of 4. So you can get a correlation for a very low Reynolds number from between 3 and 100. The Nusselt's number varies for number of this wire and so on, pipe and so on. It just varies exactly like the correlation fit. Nusselt's number divided by PrO3 is 0.82 multiplied by Reynolds number 0.4. So everything is non-dimensional. Heat transfer, one nice about this, everything is non-dimensional, so you don't have to worry about if I go somewhere else, in some other geometry. Now, the important thing is the number of fluid has been used. So water was used, oil was used, air was used, and some other air was also used, some various references. Doesn't matter what fluid and everything, it seems to fit this curve approximately. So from 3 to 100 for various geometrical shape, like it's a cross flow over a pipe or a wire or a circular cylinder. At rho Reynolds number, you can use this correlation. Understood? Everybody, any questions on that? Any question? No question? Okay. In that case, I'm going to stop recording.